Hello, we continue with lecture number 7 for Math 609. Last time we were discussing iterative methods. So let me start with a short recollection what we were discussing. We have a matrix A, and that is a square matrix of dimension n. It is non-singular, and we consider the system AX is equal to B, where B is the right-hand side, which is a vector in Rn. In order to start with any iterative method, we need to represent this system in the form X is equal to Tx plus C, where T is another matrix of dimension n, a square matrix of dimension n, and C is some other vector of dimension n. Now, this representation here is a basis of any iterative method. Various matrices T will give rise to various iterative methods. The matrix T is called the iteration matrix. And then the method that is initiated or governed by the matrix T is the following method. We start with an initial guess x0, which is a vector in Rn. So we choose x0, and then what we have is that the vector xk plus 1, the vector that we obtain at the k plus first iteration, is equal to the matrix T applied to the vector xk, which is the vector obtained from the previous iteration, plus C. So here this C is the same, and this T here is the same. And the iteration index k runs from 0, 1, and so on. So we see that when k is equal to 0, if we plug it in here, we have that x1, so the first vector that we obtain, is equal to the matrix T applied to the vector x0 plus C. This way, we start with the initial guess x0, we obtained the vector x1. Then if we look at the iteration when k is equal to 1, and substitute this k equal to 1 into the equation, we have that x2, which is the next vector of the iterative procedure, is equal to T applied to the vector x1, which we have already obtained, plus C. And this way now we have the second vector, or the third vector of the iteration x2, and so on. For a general k, we obtained that the vector xk plus 1 is equal to the iteration matrix T applied to the vector which is obtained at the previous iteration xk plus the vector C. And this gives you the new vector xk plus 1, which is also a vector in Rn. So you can view the iterative procedure, as I discussed last time, as black box, which is the following. You have an input to the black box. The black box applies T to this input and then adds the vector C and outputs the result. So if we input here x0, we will output the vector x1. Once we have the vector x1, we input it again in the black box. Then we have T applied to x1 plus C. We will have another vector x2, and so on. We input x2 again in the black box, we applied t to x2 plus c and so on. We will generate a sequence of vectors in Rn, x0, x1, and so on, xk. And if we assume that, let's say for a moment that we assume that this sequence of vectors converges, then where to what will it converge? So if we look at this equation here, and xk plus 1 will converge to, let's say this sequence converges to x. Again, it's a question whether it converges or not, but for a moment, let us assume that it converges to x. So xk plus 1 converges to x. Xk converges to x, so t of xk will converge to t of x, and c will be a constant. So if you do limit in this equation, when k goes to infinity, then we will see that the limiting vector x will satisfy the system x is equal to tx plus c, and this system was the way in which we had rewritten the original system ax is equal to b. So if the sequence of vectors x0, x1, and so on, xk generated by this iterative procedure converges, then it will converge to the point x, which satisfies this system, and this vector x is in fact the solution of our original system. Now, last time we discussed two main theorems which will assure us or will guarantee that the sequence that is generated by the iterative procedure will converge. And the first theorem was actually an if and only statement, but we will, for the sake of this lecture, we will look at only one direction of this statement. And it says that if the spectral radius of the iteration matrix T, so the matrix T here that is that is in the iterative procedure, this iteration matrix T, if the spectral radius of this matrix is less than 1, then the sequence that is generated by the iterative procedure will converge to the unique solution of the equation x is the system x is equal to tx plus c for any initial guess x0. And also we discussed last time that if the spectral radius of this iterative iteration matrix T is less than 1, then this system will have a unique solution, because if the spectral radius, let's go back to one of our theorems from last time, if the spectral radius of T is less than 1, then we will have that E minus T will be, I minus T will be a matrix that is an invertible matrix. And it was discussed here. If the spectral radius of a matrix is less than 1, then I minus T, identity minus T, is an invertible matrix. And that's why when we go back to the system x is equal to tx plus c here, if you look at this system, we can rewrite it in the form, if we move T on the other side, this is x minus tx is equal to c. If we pull out x, this will be exactly identity minus t applied to x is equal to c. And if the spectral radius of T is less than 1, then the identity minus T will be an invertible matrix, and therefore this system will have a unique solution. So it will converge to the unique solution of this system. And we also discussed a second statement that was in some way not as strong as the first statement. If the norm of a matrix T is less than 1, where this norm could be in some natural matrix norm, We do not specify which particular natural matrix norm, but if there is a natural matrix norm such that the norm of t is less than 1, then the sequence xk that converges, that is obtained by the iterative procedure, then this sequence converges to the unique solution of this system for any initial guess x0. And moreover, we also derived 2 error estimates. The first error estimate tells us how the norm, the same norm as we as the vector norm that is related to this natural matrix norm, how the norm of the error at the kth step behaves. Namely, we know by definition that the error of the kth step, this is the exact solution of our problem minus the output of our iterative procedure at step k. So this error is less than or equal to a number which is the norm of the matrix T to power K times some other number which we do not know because we do not know what X is, but this number is some constant, and this constant will depend on our initial guess. If our initial guess, which is the vector X0, is far away from the exact solution, then the norm of this difference, of this initial error that we are having, will be big. Nevertheless, so this constant will be big. Nevertheless, because the norm of t is less than 1, this number here will be a number that is less than 1 raised to power k. And so when we let k go to infinity, this constant here doesn't change because it does not depend on k. When k goes to infinity, we have that this number here that is less than 1 to power k will go to 0. And so we have that the norm of x minus xk on one side is bigger than or equal to 0 because it is a norm of a vector, and a norm of any vector is bigger than or equal to 0. And on the right-hand side, we have an estimate that this norm is bounded by a sequence of numbers which goes to 0 as k goes to infinity, and therefore the norm of the error, this vector norm of the error that was associated to the natural matrix norm, will go to 0 as k goes to infinity, which is the same as saying that the norm of x minus xk go to 0 as k goes to infinity, which is basically the same as saying that xk converges to x as k goes to infinity. Now we also discussed another norm, which is the norm, another estimate. This estimate is slightly different than this estimate in the sense that here the norm that we have on the constant that we have on the right-hand side basically can be computed. This constant here is the first iteration, the vector that we obtained after the first iteration minus our initial guess. So this is a number. The norm of this vector is a number that can be computed. And also 1 minus norm of t is another number that can be computed if when t is given. And therefore here this constant can be computed in comparison to the constant here that this constant we actually cannot compute. And again, here we see that when k goes to infinity, then the norm of t to power k will go to 0. And again, we will have that xk will converge to x. Now, remember that I did not include it here, but I will include it when I post the lecture. Remember a long time ago, when we discussed norms, we discussed that in Rn, every two norms are equivalent. So if we look at this norm here, which is a vector norm, that is applied to the error, which is associated to this natural matrix norm, then this vector norm will be equivalent, for example, to the L infinity norm. So what we have that there are some constant C1 and C2, which may or may not depend on N, such that this particular norm here is bigger than or equal to a constant C2 times the infinity norm of the error, and bigger than or equal, or C1, where C1 and C2, as I said, are constant that are strictly bigger than 0, of the infinity norm of the vector AK. So now we show that this norm here, this is where we showed it, we show that this norm of the vector EK goes to 0 as K goes to infinity, and therefore we will have that the infinity norm of EK will go to 0. So we will have that the EK, the infinity norm of EK will go to 0 as K goes to infinity. But what was the infinity norm? By definition, this was that the maximum of absolute value of the ith coordinate of EK, the ith coordinate of EK, this is the ith coordinate of X minus the ith coordinate of the vector XK, where maximum is from 1 to N, then this maximum, which is the definition of this infinity norm, will go to 0 as K goes to infinity. So what does that mean? If the maximum of some numbers of a finite number of numbers goes to 0, basically this would mean that for every I from 1 to N, we will have that absolute value of Xi minus Xik will go to 0 as K goes to infinity. And what would that mean? That would mean, I will write down here, that would mean that the Xik will converge to Xi when K goes to infinity, and this is for I equals from 1 to N. Or in other words, if we look at the vector X, which is the vector column with coordinates x1, x2, and so on, xn, which is the solution of our system. And then if we look at the coordinates of the kth iteration of the output of the kth iteration, x1k, x2k, and so on, xnk, then we have that coordinate-wise, the first coordinate of all these vectors will converge to the first coordinate of the vector x. The first coordinate of the kth vector will get closer and closer. The second coordinate of the kth vector will get closer and closer to the second coordinate of x, and so on. The nth coordinate of the kth output of our iteration will converge to the nth coordinate of the vector xn. So no matter what norm we have applied here to the matrix T, that is an induced natural norm, because we will end up with that corresponding vector norm of the error going to 0, and because the vector norms in Rn are all equivalent, then that would mean that coordinate-wise, all the components of the output, the kth output of my iteration, will get closer and closer to the components of the exact solution X of my system. If we go back to the theorem, one of the main points that we used, or the main observations that we used in order to prove this part of the theorem, which actually was a separate theorem before, was that if you look at the error at the step k plus 1, which by definition is the exact solution minus the output of your iteration. Here is only 1 plus, minus the output of your iteration is step k plus 1. Since X is the exact solution, it satisfies the system X is equal to Tx plus C. So instead of X, we write Tx plus C. And here, instead of X, k plus 1, we write the how we got xk plus 1. We got the k plus first output of the iteration as t applied to the kth output of the iteration plus c. And then once we have that, so this part here is equal to the vector xk plus 1, and this first part here in red brackets is equal to x. Now, when we open the parenthesis, this c will cancel out with this c, and then we just have the difference between the t applied to the exact solution and the t applied to the kth iteration of the output of the kth iteration of our iterative procedure. Then we pull out the matrix T, so this will be equal to T applied to X minus XK, but by definition, this is exactly the error at step K. So we have the recursive relationship that the error at step K plus 1 is equal to T at the error to T applied to the error at step K, and then we can use that recursive iterative, equation, and at the end we actually will get that. So let's use it. We have E k plus 1 is equal to T applied to E at step K. Then we can do it the same way for E at step K is equal to T applied to E at step K minus 1. And if we apply it up here, then it will be T applied to T applied to E at step K minus 1, which will give us T squared applied to E at step, which is the error of the iterative procedure at step K minus 1. And we see here that by induction, we in fact can show that E, the error at step K plus 1 is equal to T to power K plus 1, which is the matrix T applied to itself K plus 1 times the error at step 0. Or the initial error. And therefore, the norm, we can see here that if two vectors are the same, then the norms of these vectors are the same. So this norm is equal to the norm of the matrix tk plus 1 times applied to the vector is 0. And then we use this inequality between a matrix applied to a vector, that the norm of a matrix applied to a vector is less than or equal to the norm of the matrix times the norm of the vector. And then we discussed in our previous lecture that the norm of the matrix T to power K plus 1 is less than or equal to the norm of the matrix T, this number raised to power K plus 1 times the norm of the vector is 0, which is exactly the inequality that we have here, which is in fact this inequality right here, but written for step K, not for step K plus 1. Now let's discuss one more aspect. This inequality here that is written is an upper bound for the error, but it's not the best possible upper bound in the sense that it is a sort of a crude upper bound for the error at step K using the norm of the matrix T. Now, if we look a little bit more carefully, we can sort of give, in a way, a finer estimate or finer analysis of the error. In order to do that, we will use this formula, which is called the Gelfand spectral radius theorem, and we are not going to discuss it. Let me point out that we in fact showed that for every, and this is true for every induced matrix norm, we show that, and I will show you where we did that. We show that in fact the spectral radius of the matrix T is less than or equal to T to power the norm of the matrix T to power K, and this norm raised to power 1 over K. So I am going back to where we discussed all sorts of properties of the spectral radius of a matrix. And sometime if you go back through your lecture from last time, or even from the time before the last time when we discussed spectral radius, we discussed also, and we showed the formula that the spectral radius of every matrix is less than or equal to than the norm of the kth power of this matrix. And this number, the norm of the kth power of the matrix, raised to power 1 over K. In fact, a stronger relation between the spectral radius and any induced matrix norm is true. And this is this Gelfand spectral radius theorem that I cited to you. But as I said, we are not going to prove it. We are just going to use it in order to illustrate some kind of finer analysis of the error. So we will use this theorem that the spectral radius is in fact the limit of these numbers, the norm of the matrix T to power K, and everything raised to power 1 over K. And as you can see here, if we write it for K, not for K plus 1, we in fact have this estimate here that the norm, and it is right here, that the norm of EK plus 1 is less than or equal to the norm of the matrix T to power K plus 1 times the norm at the initial step. And if we write this for not for K, but for not for K plus 1, but for K, this is the inequality that we end up with. So now if we assume that E0 is different from 0 vector, because if E0 is 0 vector, so which we were so lucky that the initial guess was our exact solution, which is possible but not very probable, then E0 will be in general different from 0, and therefore the norm of E0 will be different from 0, and therefore we can divide both sides of this inequality by the norm of E0, and then we will end up with this ratio here less than the norm of the matrix T to power K. Then we can raise both sides to power 1 over K. And then on the right side, we have exactly that. And we can take the limit as K goes to infinity of this quantity. And what we have on the right side, we have that this quantity t to power k, the norm of t to power k, and this raised to power 1 over k, this quantity has a limit, and this limit is exactly the spectral radius of the theorem, of the spectral radius of the operator t, and therefore, when we look at this inequality, actually, we will end up with the limit, but this limit will be the lim sup here. I should put the lim sup is of the norm of the error at power, the error at step k divided by the error at step 0. This ratio to power 1 over k is less than or equal to the spectral radius rho of t, which basically will tell us roughly that the error at step k, the norm of the error at step k, behaves like the spectral radius to power k, because this, if we ignore the limit, the lim sup, this roughly would mean that for infinitely many k's, ek, the norm of ek divided by the norm of e0 to power 1 over k. So this ratio to power 1 over k will be roughly like the spectral radius of the matrix T when you raise to power k, and then we will have that the norm of ek divided by the norm of E0 is roughly like the spectral radius of T to power K. And when we multiply by the norm of E0, we expect to get something like that. So this is not rigorous. So from here to here, this particular two lines are not rigorous, but they give us an idea that when the spectral radius of the matrix, the iteration matrix T is smaller, then we should expect a faster convergence, because the smaller the number rho of T is, the faster the power of this number, the kth power of this number will go to 0 as k goes to infinity. So think of about the two numbers 1 over 10, for example, and 1 over 100. 1 over 100 is, both of them are less than 1, but when you start raising it to power 2, so this to power 2 will be 1 over 100. Now this to power 2 will be 1 over 10,000. And so we will have in the first case that the error at the second step, let's say, is less than 1 over 100 times some constant. And if rho of t was 1 over 100, then you would have that the error at the second step is behaves like 1 over 10,000 times some number, some constant, and therefore this error estimate or this number will be much closer to 0 than this number here. It could be closer than this number here could be closer than this, but the estimate from above that we are getting does not assure that. The estimate from above that we're getting in the case when rho of t is less than, much smaller than 1, this estimate would be better. So as I mentioned, this kind of heuristic analysis here would imply that the smaller the spectral radius, the faster the convergence we have of the output of our iterative procedure to the solution of our system. And so now this was basically, with this we end the general iterative procedure, the general iterative methods, and the the main things that we have to keep in mind is that when we have iterative procedure, we have to write the original system in the form x is equal to tx plus c. This way of rewriting the system will give us a sequence of numbers, of vectors, which are generated by this procedure, by this iterative equation, starting with some initial guess x0, when we give values to k0, 1, 2, and so on. And if the spectral radius of t is less than 1, then this sequence of vectors xk will converge to x. If the norm of the iteration matrix T, any induced natural matrix norm is less than 1, then the sequence will converge to the solution. And then we have the following error estimates, which are in a little bit, which are rougher, and we will see that in our examples. And also the idea that if the smaller the spectral radius is, the faster of the iteration matrix T, the smaller the spectral radius of the iteration matrix T, the faster we will have the convergence to the exact solution. So now we start with describing 3 iterative methods in this that we're going to discuss in this class. The first method is called the Jacobi method. And this method is based on a certain representation of the original system AX is equal to B with original matrix A in the form X is equal to TX plus C. And in this case, the matrix T, the particular matrix T that we're going to construct based on the matrix A, that will give the Jacobi method, we will denote by B sub j. So the iteration matrix of the Jacobi matrix will be denoted by B sub j. So we start with the matrix A. The matrix A has entries Aij, and for this method to work, we will want all the entries on the main diagonal to be different from 0, because as you will see below, we will have to divide by the diagonal elements, and or we would like a certain matrix to be invertible, and therefore we will need the restriction for the elements on the main diagonal to be different from 0. So this could be violated, and if we look at the original system, and if in the original system we have an element on the main diagonal that is 0, so we go back and we in fact can reorder the equations in the system. Reordering of the equations of the system does not change the solution of the system. It will only change the matrix A. So basically we are reordering the rows of this matrix, and also, so when a matrix is given to you, when a system is given to you, and you look at the diagonal elements, and if you have a diagonal element that is equal to 0, you cannot directly apply the Jacobi method. You have to reorder that system first. And second, to speed the convergence also, if you want to speed the convergence, which probably you want to do that, the equations should be arranged so that Aii is the element on the main diagonal is as large as possible. So this, in a way, kind of reminds is similar to pivoting in the Gauss elimination. So if we look at the matrix A, we represent the matrix A as a sum of 3 matrices, and this we will do for all the 3 methods that we're going to discuss. So in all the three methods, L will be the same matrix, D will be the same matrix, and U will be the same matrix as the ones that I will just discuss here. So if you look at the matrix A, and we write it as A11, A12, and so on, A1n, and then we have A21, A22, and so on, A2n, and at the end we have AN1, AN2, ANN, and we discussed that the diagonal elements are different from zero. So we represent the matrix A as a sum of three matrices. Do not be confused to think that this is somewhat related to the LU factorization of the matrix A. It is not related to the LU factorization of the matrix A. So what is this representation? We denote by D the diagonal matrix that has the diagonal elements of the matrix A. By L, we denote the lower, and it's not really lower triangular, because lower triangular would mean that we incorporate the diagonal. Here we look at the elements that are strictly below the main diagonal. So this is the matrix L, and the rest of the matrix we fill in with zero. So here the main diagonal of L and everything above the main diagonal of L is zeros. So A2, we take the elements that are below the main diagonal to construct the matrix L, and the matrix U are all the elements that are strictly above the main diagonal. So if you look at the elements that are strictly above the main diagonal, you take them away from the matrix A, and we create a new matrix U that has everything that is on the main diagonal and below the main diagonal zero, and everything that is strictly above the main diagonal are the entries of the matrix A. So this basically is used to construct the matrix U. Why do we use U? Because it is an upper triangular matrix, and actually it's more than upper triangular matrix, because on the main diagonal it has zeros. And why we denote this as L? Because it is a lower triangular matrix, and again, it is more than simply lower triangular matrix. It has zeros on the main diagonal. So once we have this representation for a matrix, for the matrix A, we go back into the system AX is equal to B and write down what A is. So we go at, we look at the system AX is equal to B, and as I said, we write A as this strictly lower triangular part, the diagonal part, and strictly upper triangular part. And what we decide to do, we decide to, we multiply here all these matrices by X, so we'll have LX plus dx plus ux is equal to b, and then lx and ux go on the right hand side with a negative sign, and we pull out x from them. So what we end up with is dx is equal to minus lx minus ux plus b, and then we pull the minus sign and the x, and this is exactly what we are going to get. Now, remember that when we looked at the matrix D, it had all the diagonal elements, and all the diagonal elements were different from zero, and therefore the matrix D will be an invertible matrix. So we can multiply both sides of this equation by D inverse. And what will be the inverse? Remember that when if you have a diagonal matrix with non-zero entries on the main diagonal, so we have here 0, 0, then what would be the inverse of that matrix? The inverse of that matrix is again a diagonal matrix, where on the main diagonal you will have the reciprocals of the main diagonal here. And indeed, if you look at D multiplied by this matrix, which I claim is the D inverse, then A11 will be multiplied by 1 over A11, so you end up with 1, and so on. A and N will be multiplied by 1 over A and N, and you will end up with 1. So the result will be that on the main diagonal, you have all 1s. And outside of the main diagonal, we will have all 0s because of the fact that you have a multiplication of 2 diagonal matrices. So indeed, this matrix D is invertible. And if we multiply both sides by the inverse, we have to multiply this vector here. And also we have to multiply the vector B. And if we look at that, that looks like rewriting the system AX is equal to B in the form X is equal to some matrix TX plus C, where this is the matrix, the iteration matrix, and this is the vector that is added to this iteration matrix applied to X. So now this way of rewriting the system AX is equal to B gives the Jacobi iterative procedure, and that's why this matrix here we don't denote it by just generic T, but we denote this iteration matrix by B sub J, and this is the Jacobi iteration matrix. So the Jacobi iteration matrix, if we want to write it in a matrix form, it is actually minus the D inverse, which is the inverse of the diagonal matrix that consists of the diagonal elements of the original matrix A, times the sum of the matrix of the two matrices L and U, and the vector C in this iterative equation, the vector C in this iterative equation is equal to D inverse times B. So this is the iteration, and this iteration is called the Jacobi method. So this is how, using the Jacobi method and starting with some initial vector x0, which is our initial guess, we will generate the sequence of successive approximations to the vector x, hopefully successive approximations to the vector x, because we do not, in order to have convergence here, we have to have some conditions on the matrix Bj. Not every sequence, not every matrix A will give you a matrix Bj that has a spectral radius, for example, less than 1, or a matrix Bj for which the some induced matrix norm is less than 1. So now, usually when we write the Jacobi method, we do not write it in this form. We leave the D on the left-hand side. So we write it as, we look at this system here, and everything that is on the left-hand side, we give an index, a superscript K plus 1. Everything that is on the right-hand side, we give a superscript K. So this is how we usually write the Jacobi iterative procedure when we do not multiply both sides by D. And we will illustrate this on the particular example here of a 3x3 system. So we are given a system with a matrix A that is a 3x3 and entries say 1, 1A, 1, 2, and so on. And if we would like to write how the Jacobi will look like in for this particular case, we do the following. We look at the elements on the main diagonal. These are the elements that are on the main diagonal. And then we let them on the left-hand side, and we associate with all the x's that are associated with the a's that are on the main diagonal. We give to these x's index k plus superscript k plus 1. So to this x2, we will give superscript k plus 1, and to this x3, we will give a superscript k plus 1. And then what will happen for the rest of the axis, so this one we will move on the right side, and we will give a superscript k. So this is a superscript k, and this is a superscript k. So this one and this one will go on the right, and we'll have a, whenever you have x associated with a matrix entry that is off the main diagonal, we will give it a superscript k, and here superscript k, and move it to the right. And indeed, if you see here, this is exactly what happened. Everything that is on the main diagonal stays on the left, and the indexing, the superscripts are k plus 1. We have the right-hand side, and everything that is on the left that is offside the main diagonal goes to the right and has a superscript here. The superscript k is in here, and it has a superscript k, which basically corresponds exactly to this representation and writing this equation in a matrix form. Now, if we wanna see what is happening, basically, if you start, for example, with the vector x0, and we would like to compute the vector x1, the vector x1 has components x11, has components x21, and has components x31. And we directly, if you use the components of x0 and to compute the right-hand side, we, from this system, we directly express the first component of x1, the second component of x1, and the third component of x1, just by dividing by respectively a11, a22, and a33. And in general, if we have in our hands the vector xk, then we will have the first component of xk, we will have the second component of xk, and we'll have the third component of xk. We come to the right, everything here that is on the right side will be known, because all these components that are the coordinates of the kth vector will be known, and therefore in order to compute the first component of k plus 1, we just have to divide this expression by a11. For the second component, we have to divide this expression by a22, and so on. At the kth step, we have the vector x1, x2, x3 kth, the kth vector, and we compute the first, the second, and the third component of this vector. And we can illustrate this on a particular example. So we have this simple 2x2 matrix, and we would like to, let's say, compute its solution. We see that the exact solution is the vector with coordinates 1, 1. And if we want to write the Jacobi iterative procedure for solving this system, we look at the elements on the main diagonal, we leave them on the left side, and we rewrite them with index k plus 1 and k plus 1, and everything that is of the main diagonal, we move to the right, and we associate it. You see here minus x2 is moved to the right, and minus x1 is moved to the right, and we associate it with index k. And if we make this little table, if we start with an initial guess, the vector with component 0, 0, and so at iteration k equals 0, at step k equals 0, we start with 0, 0, and then what will be the error? The error will be x minus at 0 step, at the initial step is the vector 1, 1 minus this vector 0, 0. So the vector will be with components 1, 1. And if we decide to look at the infinity error of the infinity norm of this error, the infinity norm will be 1. Then after the first iteration, when we put here 0, 0, because when k is equal to 0, those components will be 0, 0, then we will have 2 x1, 1 is equal to 1, and then we will have 2 x2, 1 is equal to 1. This is the Jacobi iteration for k is equal to 1. So we see that now the new vector will have components 1 half, 1 half. So this is the first and the second component of x1. And then what will be the error? The error will be x, which is 1, 1, minus 1 half, 1 half. So the error will be the vector 1 half, 1 half. And therefore, the infinity norm of this vector will be 1 half. Now, when we apply this iteration for k is equal to 2, then we can compute the right side exactly. So then we'll have x2, x1, 3. Now the third, is it when k is equal to, no, this is here when k is equal to 0, we get the first component. And when k is equal to 1 here, we get the second component, the second vector. So we have 2x1, 2 is equal to 1 plus x2, 1. And we have 2x2, 2 is equal to 1 plus x1, 1. X2, 1 is equal to a half, and x 2, 1 is equal to, and x1, 1 is equal to a half. So 1 plus a half is 3 halves, and 1 plus a half is 3 halves. When we divide by 2, we have that the coordinates of the vector x2 are 3/4 and 3/4, and therefore the error will be the exact solution 1, 1 minus 3/4 and 3/4, which is the vector with components 1/4 and 1/4. So this is the error at step 2, and you see that the infinity error will be 1/4. And then not finally, but finally for actually computing this table, when k is equal to 3, in this particular recursive relationship will be k is equal to 2, because then we will get the x3. Then we will have 2 x1, 3 is equal to 1 plus x2, 2, and x2, 2 is 3/4, and 2 x2, 3 will be equal to 1 plus x1, 2. So x1, 2 and x2, 2 are 3/4. So this will be 1 plus 3/4, which will be the 7/4. And here, this will be also 7/4. If you divide by 2, you will have 7/8 and 7/8. And then the error will be the vector 1, 1 minus 7/8 and 7/8. And therefore, the error will be the vector 1/8, 1/8. This is the error, the error, which is x minus x3. And the error will be, the infinity norm of this error will be 1/8. So if we look at the construction of the matrix, that is the Jacobi matrix, iteration matrix that corresponds to the matrix A, and we look at the formula for Bj. Remember that the formula for Bj was minus d inverse L plus U. So let's go back here and write down what Bj is in this particular case, minus. The matrix D is a matrix on the main diagonal. So the inverse, as we discussed, is the reciprocals of the elements on the main diagonal. So it will be 1/2, 1/2, and then 0, 0. We have the negative sign in front because we have it here. And then L plus U, basically this is the matrix A if you take away the main diagonal, which is this. And if you do, once you do the multiplication of those two matrices, you will see that this term is 0. Then this row multiplied by this column will give you -1/2. With this minus will give you +1/2. Then here you'll have again 0 times 0 plus 1/2 times -1, which will give you -1/2. With this minus will give you 1/2. And then 0 times -1 plus 1/2 times 0 will give you 0. So this will be the matrix Bj that would correspond to the matrix A in the Jacobi iteration. And if you look at this matrix and you see that the you compute, for example, the infinity norm, then how do we compute the infinity norm of this matrix? We learned to do that. I believe it was one of your homework problems. So we look at the sum of the absolute values of the components of the first row. We end up with a number. The sum of the absolute values of the components of the second row, we end up with a number, and we take the maximum of this number, and we see that it is 1/2. Now, if you go ahead and find the spectral radius of this matrix, so we have to compute 0 minus lambda, and then 1/2, and then 1/2, and 0 minus lambda, and you compute the determinant of this matrix and find the zeros of the determinant of this matrix, which is a polynomial of degree 2 in lambda. So we'll have this times this, which will be lambda squared minus 1/4. This is the characteristic equation, which will give you that lambda 1 is equal to 1/2, and which will give you that lambda 2 is equal to -1/2. Now, to get the spectral radius of the matrix, you have to look at the absolute values of the eigenvalues. So absolute value of 1/2, absolute value of -1/2. This will give you the numbers 1/2, 1/2, and you have to find the maximum in order to get the spectral radius. So you will get that the maximum is 1/2, and this is the spectral radius of this matrix Bj. So we see here that in this particular case, the infinity norm is the same as the spectral radius, and both of them are 1/2, and both of them are less than 1. And therefore, using our theorem, any of the theorems, because both of those are less than 1, we will see that the Jacobi method converges for every initial guess x0. So here we chose an x0 to be 0, but if you choose another initial guess, then you also will observe convergence because it will follow from the theorem. And if we apply this particular estimate here, which is the Kruder error estimate, that you have that the error at step k is less than or equal to the norm of the iteration matrix to power k times the initial error. Here we have the exact solution, so we can actually look at the error at the step 0, and we can look at the error at any other step. But if we look at this error estimate, then we have that error of the iteration at step k plus 1, the infinity norm of this error is less than or equal to the infinity norm, here should put infinity norm of the matrix Bj to power k plus 1 times the error, the infinity norm of the error at the initial step. And the infinity norm of Bj is 1/2. So this is the inequality that we have for the error. And as you see here, 1/2 as k goes to infinity, 1/2 to power k plus 1 will go to 0, and therefore the infinity norm of the error will go to 0, and therefore you will see here that each of those coordinates x1 will go to the first coordinate of the kth iteration is as k runs through 0, 1, 2, and so on is 0, 1/2, 3/4, 7/8. So these are numbers which will get closer and closer to 1, which is the first coordinate of the exact solution. And then if you look at the second coordinate here, they are 0, 1/2, 3/4, and 7/8. And if we continue computing for the other case, we will see that this also will go to 1 as k goes to infinity, which is the second coordinate of x, the second coordinate of the exact solution. So now let's, in this particular case, and this will be the only case in which we actually explicitly can write down the formula for the matrix B, the iteration matrix. So the Jacobi iteration matrix will be the only case when we write this matrix explicitly. If the original, remember that the formula for the Jacobi matrix was minus D inverse multiplied by L plus U. And remember that D inverse was the elements on the main diagonal, their reciprocal values. So what we actually have, we have minus, and then we have 1 over A1, 1 over A2, 2, and so on. We have 1 over A and N, and everywhere else we have 0. So this is the inverse of the matrix D. And then this matrix will be multiplied by the L plus U. What is L plus U? This is the original matrix A, but taken away the main diagonal. Namely, on the main diagonal, you have zeros, A2N, and at the end, you will have AN1, AN2, and so on. You will have 0. So this here is the matrix L plus U. Now, if you do this multiplication, you will see that to get the first row of the matrix Bj, you have to multiply the first row here by all the columns of the matrix L plus U. When you do that, everywhere where the zeros here will meet the second, third, and so on components of all the columns will make them 0. So basically what you will end up with, you will end up this row multiplied by minus 1 over A11. And this is exactly what we have here. This is the first row of the matrix A, where on the position where the main diagonal, where this row hits the main diagonal, you have 0. So you have A12, A13, A1N, and then all these elements are divided by the element that was supposed to stay on the main diagonal, A11, and then you have in front minus 1. And then what's happening for the second row? The second row of Bj is obtained by multiplying this second row. And why do we have the minus? Because of this minus in front. It's the second row of the matrix D inverse multiplied by all the columns of the matrix L plus U. And because of the fact that D inverse is diagonal matrix, as a result, you will have the elements on this row, on the second row, divided by A22, and then with a negative sign in front. And this is exactly what you got, what you're having here. You look at you are having the elements of the entries of the matrix A, A21, A23, and so on, A2N. This whole row is divided by A22, except on the main diagonal, you have 0, and then you put in front negative sign because of this negative sign. So this is how you can visualize the matrix Bj for any matrix A that you start with. If you have the system AX is equal to B, you start with some matrix associated to this system, and you can directly in explicit form write what Bj is. When you do a programming, which you will have to do for your homework, you never in fact write explicitly the matrix Bj. You implicitly, when you write the code, you implicitly do the recursive relationship. In the recursive relationship, you implicitly use the matrix Bj, but you almost never, except for theoretical purposes, you write it in this form. So this is what the matrix Bj is, and we will use how the matrix Bj looks like in order to prove the following theorem. And the theorem is the following. So if you have the system AX is equal to B, and if you know that your matrix A is a strictly diagonally dominant matrix, then the Jacobi method converges for any initial guess X0. So let me recall what was a strictly diagonally matrix, strictly diagonally dominant matrix. So if you have the matrix A with components A1, 1, A1, 2, and so on, A1n, A2, 1, A2, 2, A2n, and so on, AN1, AN2, ANN. A matrix to be strictly diagonally dominant means for every row of this matrix, if you look at the element on the main diagonal, it dominates the rest of the elements. So here the element on the main diagonal is A1, 1. So absolute value of A1, 1 is strictly bigger than the sum of the rest of the elements, which are of the main diagonal, A1, n. If you look at the second row, the element on the main diagonal is A2, 2. So this element dominates the rest. What does it mean? That the absolute value of A2, 2 is strictly bigger than the sum of the rest. So the strength of the rest of the elements is not big enough to overpower the element on the main diagonal, A2n. You can try to remember this way. And at the very end, this is the element that stays on the main diagonal. So it is a very strong element. The absolute value of ANN is strictly bigger than the absolute value of AN1 plus all the elements that are of the main diagonal AN and minus 1. And of course, it can be rewritten in the summation notation that the absolute value of AII is strictly bigger than the sum of the absolute value of AIJ, which are the sum of the rest of the elements on this row. When j is from 1 to n, this means the rest of the elements, but except the element on the main diagonal, and that's why you write j is different from I. In order to prove this theorem, basically the theorem will be based on some other theorem. We have to compute, or we will compute, the infinity norm of Bj. And we will show that if A is strictly diagonally dominant, that the infinity norm of Bj is less than 1. And then using one of our theorems for a general iterative procedure for solving systems, if some induced matrix norm is less than 1 of the iterative of the iteration matrix, then we have that the sequence of vectors that is induced by this iteration process will go to the exact solution as k goes to infinity for every initial guess. So our main goal here, after which we invoke a known theorem, is to show that the infinity norm of the matrix Bj is less than 1. And in order to do that, let's first look at the matrix Bj. We know how the matrix Bj looks like. And we also know how to compute infinity norms of matrices. So how to compute infinity norm of a matrix? We know that we look at if with B1, let me see how I wrote it. Yeah, if with the matrix Bj, we assume that, let's denote its entries by Bij, and we here have formulas for Bij. So the sum of the elements on of the absolute values of the elements on the first row, we sum them in absolute value. Then we sum the absolute value of the elements on the second row, and so on. And then we take the maximum of them. This is what we found that is an easy way to compute the infinity norm of a matrix. So we look, let's say, at the row I. We look at the sum of Bij when j is equal from 1 to n. Then we run I from 1 to n, and this was the definition of the, not the definition, but this was a way to compute the infinity norm of a matrix. Now, this maximum, because it runs from 1 to n, is achieved for one of these indices. So when we look at the rows here, there is some index of a row I0 for which the maximum among all of the L1 norms of the rows is achieved, and therefore this maximum is actually equal to some Bi0j for j is equal from 1 to n. And now let's go and see how the elements Bi0j of the matrix Bj look like. So what is on the element I0, on the row I0, what do we have here if we look at the matrix Bj? So we have minus, we have AI01, because this is the element of the original matrix on row 1, the first element on row 1 of the original matrix. And then we have to divide by AI0, I0. This is the first term, and I wrote it here in absolute value, plus and so on. And we see here that we will have all these terms here, but except that at the middle where this row I0 hits the main diagonal, which is on position I0, I will have 0. So that's why I'll have AI0, I0 minus 1, which will be the I0 minus 1 column, divided by AI0, A0. Then if I look at the column, at the row, the element of the row that corresponds to column I0, I'll have 0, and then it will be plus AI0, I0 plus 1, and so on. So this will be the sum of the absolute values of the elements on the ith 0 row of Bj. And you see here that we can pull out the absolute value of AI0, I0 from the bottom. So it is 1 over AI0, A0. And what will be on the top will be the sum of the absolute values of the elements that are away from the main diagonal. And according to the definition of a strictly diagonally dominant matrix, the absolute value of the element on the main diagonal is always bigger than the elements on that row that are than the sum of the absolute values of the elements that are on that row, but they are away from the main diagonal. And this is exactly what is written here. So we have that this is less than 1 because the matrix is strictly diagonally dominant. So we have proved the theorem, and every time now when we have to solve a system that has a strictly diagonally dominant matrix, we know that if we use the Jacobi method, then we always, no matter what initial guess we start with, we will always have that the sequence of vectors that we generate will get closer and closer to, as we increase the number of the iterations, we'll get closer and closer to the exact solution of our system. And we can write the Jacobi algorithm. In the Jacobi algorithm, if you go back to what we had for the 3x3 matrix, you see here that you actually have to have two copies of the n-dimensional vector, one copy where you keep the kth version of this vector, and another copy when you actually compute the k plus first iteration. And so if we call this an old, which is the value of the iteration at step k, and we call this new, which is the value of the vector, which is the vector obtained at iteration k plus 1, then in fact we can write the general algorithm. We set to x old to be equal to x0, which is our initial guess. Remember here, x old is a vector in Rn, and then we compute every component of the new vector, which is the k plus first iteration, the components of the vector xk plus 1. This is the ith component of the vector xk plus 1. It is the bi minus the sum of the aij's times the xj all divided by aii. And if you basically come here to see how it looks like when we do the 3x3 matrix, this is exactly to find the first component of the new vector. So this is x1 new. This is the right-hand side minus the elements of the entries of the matrix multiplied by the corresponding coordinates of the old version of the vector, but you don't have a11 times x1, so all the elements that are of the main diagonal, and then you divide by a11. So if you look at this, and you can see that in fact this is exactly what the algorithm is doing. And then once you do that, then the old becomes new. Now the version that you have, the k plus first iteration, will be now old one, and then you will compute the k plus second iteration which will be the new one. And if we decide to, we need two variables which are one-dimensional arrays which are vectors in Rn. So the two variables are the x old and the x new at all times, which is something that is slightly different between Jacobi and the next method that we're going to discuss, which is the Gauss-Seidel method. And let's do the operation count per step. So if we look at the multiplications, how many multiplications do we have? At every step here, we compute, so at this step, we compute all the components of the vector x new. In order to compute the first component of the vector x new, so when I is equal to 1, we have here n minus 1 multiplications, because we have every element. So if, for example, we write it, it will be for the first component. So I here is equal to 1. When I is equal to 1, we have b1 minus, and then it will be j is different from I, so it will have 2, and then j, it will be the vector x2 old times the component x2 a12 times the component a12. Let me see here, a11 x1, and then we will have plus a12 x2. So I will have a12, and then minus a13 x3 old. and then minus and so on, A1 n x n old. So this is how the first component will be. This is the x1 new, and then this whole thing will be divided by A1 1. So what we'll have here, we'll have from 1 to from 2, 3, and so on, n, you will have n minus 1 multiplication. So this is 1, 2, and so on, n minus 1 multiplications. And then 1 minus 1 multiplications will be in this sum here. And for every I, you will have n minus 1 multiplications, but the i's are n. So the number of multiplications will be n times n minus 1. For every I, we have one division. This is once you do the multiplications, then you divide by I. So you will have one division for per every I. So you will have n divisions. And if you look at so we either can count multiplications and divisions, and if we count the multiplications and divisions, and you look at the highest power of n, then this will be of order n squared. Or if we, here should be approximate, or if we decide to count as they sometimes do when they talk about floating point operations, if you count also additions and subtractions. So let's count the additions or subtractions. You see here that we will have how many additions. We have n terms here, or subtractions. We have n terms here. So this is a total of n terms. And between every two, we have addition or subtraction. So we have one here, we have one here, and so on. At the end, we have one here. And this way you will have n minus 1, because, for example, if you have 2, you will have one subtraction or addition. If you have 3 terms, then you will have 2. So if you have n, you will have n minus 1. So for computing xi, you will have n minus 1 subtractions, and then I from 1 to n, so you will have n times n minus 1 additions or subtractions. And then if you add this total number, and you look at the leading terms, you will have n squared from here, and you will get n squared from here, and therefore the total will be 2n squared. And I will just finish with this. Now, when we write this algorithm here, we did not talk about stopping criteria. So what could be a stopping criteria? There are various ways about determining when to stop. You can set in advance a certain number of iterations. So we can say, well, I don't want to make more than big N iterations. And then you will run this loop here until x new becomes when you set a counter, until you count a certain number of iterations n. Another way in to stop computing your sequence of iterative approximations to the solution is when you want 2 consecutive outputs of the iterations to be close enough to each other according to a prescribed accuracy. For example, x new, this will be x your xk plus 1 minus the x old, which will be your xk, divided by the norm of this, divided by the norm of xk. You would like this to be less than a certain prescribed in advance accuracy. Or if you look at the residuals, remember that the residual at step k was the right hand side minus a applied to the output at step k. This is by how much it measures, by how much the xk fails to satisfy the system, and the ratio of the residuals is smaller when the ratio of the residuals is smaller than a prescribed accuracy. For example, if you have rk divided by r0 is less than epsilon, or then this is another way to stop the iteration. Okay, this is the end of this lecture. The next lecture will discuss Gauss-Seidel and the SOR method. Thank you.